always follow the path of least resistance? Hey, Cox, when you're reading it, just skip over the word magnitude. Just skip it. Isn't that what it's asking for? They're saying how much. They're saying how much. Magnitude is how much, right? What is the frictional force? What? No, for number 6, you would also be using the weight equation.
No, you said Friday.
I love how Riddle likes to ask questions that I've already answered. What? 7.
It's meters per second squared. It's the question below it.
Acceleration.
How do you know which one's it?
All right, here we go. Shh. A lot of extra time, so you guys are probably wrapping it up. You're coming across the last couple that you don't know. So here we go. Shh. Zzz, zzz, zzz. So I'm going to go one by one through these. You tell me if you want me to work it. Even if you did it and you just want to see how I do it, that's fine. I'll probably do it the same way as you. I'm going to go each question at a time. Number 1. Anybody need me to work it?
You just say the answer.
No. You need me to work number 1. Okay. Guys, I want to take my time on this. I don't want to gloss over it. Number 1 says we have a car speeding up. Stop. What should our answer be as far as the number? From 5 meters per second to 25 meters per second. What is our, well, I'll just finish reading the question. In 10 seconds while traveling in a straight line, what's the car's average acceleration? If we're looking for acceleration and we have meters and seconds, what is our unit going to be in? Squared. Meters per second squared, because it's acceleration. Acceleration has 2 units of time. Okay? So it's going to be a positive number of meters per second squared. Okay. We know what we're looking for. If we come up with a negative number or some different unit, we did something wrong, right? All right. It says we're going from 5 meters per second, so that makes it our what velocity? Initial velocity. To 25 meters per second, which is our final. Which one do we put in the numerator first?
25.
The final. Okay, so acceleration is equal to change in velocity, which is Vf minus Vi divided by t. Does everybody understand that?
Yeah.
Okay, so the next step, we're still looking for acceleration. We have 25 meters per second minus 5 meters per second divided by, what's the time? 10 seconds. Okay, so we keep going down. We'll solve for the numerator. 25 minus 5 is 20. 20 what? Meters per second. That's the change in velocity divided by 10 seconds still. Okay, what's 20 divided by 10? 2. 2 what? Meters per second. Per second. Or, since it's the same unit of time, we can square it. If it was a different unit of time, for example, if we were talking miles per hour, we'd say miles per hour per second. Right? Because in common language, don't we use miles per hour for car speed? But you'd still want to use seconds if you're talking about the change in miles per hour every second as you're applying the brake or the accelerator pedal. Okay? Does our answer fit in there?
Yes.
It's what we were expecting as far as the units and the positive or negative. Good?
Yes.
Okay, I know he's talking to you, but it looked like it was on topic, right?
Yeah, well,
So I'm kind of sort of okay with it. Try to stick with us. All right, everybody good on number 1? All right. Is number 2 essentially the same question?
yes.
Do we need to do number 2?
No. But
Can you give us the answer?
All right, we'll do it. We'll do it without being on the board. Skateboarder slows down. What's our negative going to? What's our answer going to be? Negative. From 12 meters per second to 4 meters per second. So our numerator is going to be. Our numerator is going to be 4 minus 12, which will be negative 8. What? Meters per second divided by 4 seconds. What's our answer going to be? Negative 2 meters per second squared. Good. Everybody good?
Yes.
Number 3, weight. An astronaut has a mass of 70 kilograms. Isn't that his weight? No, it's his mass. What is, what? Go ahead.
I know like on the paper it says that, but what is it?
Well, mass is a measure of matter. The amount of mass, the amount of matter. Weight is dependent upon the gravity being exerted upon the mass. The reason, guys, the reason we commonly use kilograms as weight is because as long as you're talking about on Earth, it works. Because we have a common reference to the gravity. The gravity, anywhere you go on the surface of this planet, is within like thousandths probably of 9.81 meters per second squared. Does that make sense? By the way, there are places like I was reading about northern Canada, I think. There's the Earth is actually like depressed there. So there's less mass. The density is lower. Therefore, over that part of the Earth, gravity would be actually a little bit less. Does that make sense? So it'd be like 9.805. Okay? In more dense areas, perhaps it might be 9.815. Make sense? But on average, it's going to be about the same. So if gravity is about the same, because Earth is nearly a sphere, right? Then we in common use, we can just say kilograms. Yes. Yep. Yes. Yes. He said, if I wanted to lose weight, could I move to that part in Canada where gravity is reduced? Yes, it would work. 100%. You'd still have the same amount of mass. But if the scale is calibrated, if the scale is calibrated to one part of the Earth and you move it to another part, your weight might be either more or less, depending on how the scale is calibrated. Okay, does that answer? Okay, so number 3 says an astronaut is 70 kilograms, has 70 kilograms of mass. What is his or her weight on Earth where acceleration due to gravity is 9.8 meters per second squared? How did you get it? Which formula did you use? The weight formula. Okay, we're going to use the weight formula. Weight is equal to, we have the mass, 70 kilograms, and we have the gravity, 9.8 meters per second squared. Multiply them together, and what did you get? 686 what? 686 what? Okay, so I'm hearing 686 kilogram. Guys. It's 686 newtons. Or 686 kilogram meters per second squared, right? Because a Newton, guys, an equal sign, you could also read it as is, can't you? A Newton is a kilogram meter per second squared. And sometimes you want to write it that way. Huh? No. A Newton specifically is kilograms times meters per second squared. Has to be. Otherwise, it's not a Newton. You could invent another unit if you wanted to. But we're going to use this one. Okay, because it's the standard. People a long time ago figured out, hey, we're going to use this as a standard. If we all use the same system, it makes it easier.
How come the USA created their own system?
We didn't create that system. Do you guys know the story behind the pounds and the inches and the feet and the yards versus, right, the metric? You guys know that story? You want to hear the story? Don't forget your question. Okay, so the U.S. during the time of the Revolution, the colonies forming the new nation, yes? Everybody follow? It was during the time of the Enlightenment, yes? So that New Age thing that was going on in Europe was also happening in the U.S., or the future U.S. And the founders they planned to start the country with metric system. So why didn't we? Because around the same time, who else was going to use the metric system? Britain, the future United Kingdom. Great Britain was also like, we're going to, well, what were we doing from or against Great Britain? Starts with an R. We were rebelling. So if our parent country that we no longer want to be a part of, we're rebelling against them, says they want to do what we were about to do, are we going to want to do that? So why did we stay with inches and feet and yards? Out of spite. Out of spite. Now, are there practical reasons also? Like, would we have to have, like, everybody's going to have to buy a new scale, right? Or whatever. Sure. But it'd be a one-time expense, wouldn't it? And we'd be good to go. But at the time, part of the reason we did it, part of the reason we didn't do what we had intended to was spite. Pure and simple. How many of y'all have ever done something out of spite? Is that a good reason to do something?
Yes.
Might make you feel better in the moment. It's an emotional choice. Coriel, what was your question?
Oh, so like say in basketball, I can grab the rim right now.
You can?
Yeah.
Good for you.
That's pretty good.
I used to be able, at my peak, I was able to like just barely get my middle fingertip to go boing.
I can hang on it. And but say if I move your hand in it, would I be able to?
It wouldn't be enough to make that kind of a difference.
So it's just really tiny.
It's minuscule. So the instrumentation that detected it was in orbit. They were so the orbits of orbiting satellites. Riddle, I'm trying to answer his question. So the orbits were actually deflected by the change in gravity slightly. It was detectable based on that. And then they put other instrumentation in to confirm it. Okay, what are we on? 4. Is 4 the same as 3? Do we need to do 4? Do you want me to just quickly do it? No, not even? Okay. 5. Well, I can't just tell you the answer. I haven't memorized it. I have to work through it. So number 4, a toolbox with a mass 18 kilograms. What is the weight of the toolbox on the moon where acceleration due to gravity is 1.6 meters per second squared? Mass times acceleration. So 18 times 1.6 gives us 28.8. And it's going to be in newtons, or it's going to be in kilograms, meters per second squared. What?
Are these going to be on the board during the test?
Already asked and answered.
Yes. Yes.
Come on, Seth.
You love answering or asking questions that have already been. You know why you ask questions that have already been answered?
Because you don't pay.
Because you're in your own world. You're yapping about something else all the time. All right, here we go. Number 5. How many of y'all were like struggling with number 5 and 6? Okay. It's because it's a two-parter. It got you because you thought you didn't have all the pieces you needed, but you did. It was just a two-parter. All right, here we go. A 10-kilogram box. How many of y'all, it's helpful to see a visual representation? No.
No.
Anybody? I don't care. I'm going to do it anyway. All right, we've got a box. A perfectly shaped cube. No, that's okay. 10 kilograms. Yes? And we have a horizontal floor that it is resting upon. And it is, actually it's not resting upon it, it is sliding, we're told, right? I'm going to use a jaggedy, squiggly line between that surface and the box to represent the friction coefficient, okay? The friction coefficient is all about describing how smooth or rough the two surfaces are compared to each other or whatever as they slide past, yes? Okay, so a lower friction coefficient means you've got smoother surfaces. A higher friction coefficient means you've got rougher surfaces. Does that make sense? So if you want it to slide easy, you want a lower friction coefficient. Okay, cool. So we are told the friction coefficient, this mu, is what? 0.30. Okay, we're given that. We're also given the mass. Okay, what are we looking for though? It says, what is the magnitude of the, guys, magnitude just means what's the number you're going to put there. Okay, so what is the frictional force acting on the box? As it's sliding, how much frictional force is there? So frictional force is FF, right? FF is equal to, our formula over here says, the friction coefficient, which is 0.30, times normal force. Okay, well, normal force, what the heck is normal force? Anybody? Anybody? Go.
The normal force is like the force, like the weight of the object, basically.
Almost. I'm splitting hairs by saying no. Why am I splitting hairs by saying no?
Because it's the pushing back.
Yes. Shh. The weight of the box. Okay, I'm going to draw an arrow down over here for the weight of the box. The weight of the box is pushing down. The normal force isn't the weight of the box. It's the force pushing back against the weight of the box. But because because the box isn't going up or down, we know they must be equal. So that's why I'm splitting hairs. Because it is the weight of the box, but it's not. It's the equal and opposite to the weight in the box. So we need to find the weight of the box. Normal force is the equal and opposite of the weight. It's just in the opposite direction. So if acceleration due to gravity, G, because now we need to incorporate the weight formula. Okay, we're using both of these down here. So to find G, well, we're given G, aren't we? We know on Earth that's 9.8 meters per second squared. And we have the mass. Well, acceleration times mass times acceleration, gives us the force, the weight force. 98 newtons. Hold on. Just hold on 1 second here. I think for this one, we can leave it in newtons and it'll work for us, okay? So I just plug that over here. 98 newtons. What's 0.30 times 98? So our frictional force, our force of friction is 29.4 what? Newtons. How do I know it's newtons? Because that's the only unit in our math. It's the only unit there. The normal force is the equal and opposite to the weight of the block. So when she said normal force is the weight of the block, well, it's the equal and opposite to it. So the number would be the same, but it's applied in a different direction. In practice, can you just say it's the weight of the block? Technically, is that true? No. No. If I push on this wall, am I pushing on the wall right now? By leaning on it. Is the wall pushing back with the same force? So that is the normal force. in my relationship with the wall right now. My force on the wall isn't the normal force. The force of the wall back on me is, but it's the same number. Does that make sense? It's the same value. What?
This might be stupid, but you know how when you use this like a square for gravity?
Yeah.
How come I don't do anything with the square? Because technically the square would be 9.8 times 9.8, which would be 96.04. Because technically in algebra, this square you use.
No. So you're going to apply this to another number. This gets applied to another number.
But the square doesn't matter.
It does. It tells you the square is the second unit of time. So the speed by itself in any instant just has 1 unit of time. But for each second, it changes a certain amount.
But doesn't square usually mean a thing times itself?
Yes, but we're applying this with another number.
Now I'm
Do we need to do another? We glossed over it. It was in the CK12s. Do we need to do another like falling object equation? Do you remember when we threw the rock up and then it came down? We did the whole displacement thing.
I wasn't here,
Oh, you weren't here for that? Okay.
but you said that the square means you have two measurements of time. So are the times being multiplied together then? Because the square means
Yes, the times, but you have to have another number to apply to it. You have to. All right. Well, do you want to work a problem tomorrow with that? Okay. All right. Are we good on this one? If we're good on this one, is it the same or close to?
yes,
Is the next one the same?
yeah.
Okay. That was 5? Yeah. 6, we just change it to 5 kilograms and we change the friction coefficient. Otherwise, it stays the same. Okay? So yeah, you'll come up with a different answer, but the process will be exactly the same. Okay, Races?
Yes.
All right. Oh, gosh. What's next here? Did I take attendance?
Yes.
Yes.
I did. Good. Whew. Are we on 7? A net force. Oh, this is easy. How many of you all thought this was pretty easy?
Yeah.
I hope. We'll go fast on this one. If you want me to, I can put it on the board. A net force of 20 newtons. So we're given the force. We want the acceleration. We're also given the mass. Guys, we're going to use this formula, aren't we? But can we rewrite it before we even do it? We're looking for what? Acceleration. So could we make it equal to acceleration? Yes. Okay. Now, if you look at this, what would I have had to do if I left it in this form? I'd have to get the A by itself. How would have I gotten the A by itself? I would have divided the mass out, right? But I'd have to do it to this side too. So you know it'd be force divided by mass. Okay. So set it up that way to begin with. Now, you just plug the number straight in. You don't have to do any swishy because you already did it to begin with. You switched the formula around before doing it. Okay, this is the same as this. It really is. The relationship is no different. Make sense?
It's like a triangle.
Yes, I've heard it called the triangle before. Could, if I wanted, let's say I wanted to find mass. What's mass equal to?
Force divided by acceleration.
There you go. Force divided by acceleration. Questions on that? So if we're given the newtons, the force, and the mass, we're going to use this one. It was 20 divided by 4, which is 5. And it's 5, we're looking for acceleration. Guys, hold on. This is actually good. This is the one that we actually see it on, okay? Let's do this one. Force is 20 newtons, right? And we have 4 kilograms. I want to show you something What if we wrote it 20 newtons? No. 20 what? Kilogram meters per second squared. Because a newton is a kilogram meter per second squared. Watch how helpful it can be to actually write that out. When I do the math, the numbers become, what's 20 divided by 4? 5. But the kilograms go away, leaving only the meters per second squared. Does that make sense? So if you remember that they're kilogram meters per second squared, it helps you get to the correct unit, even if you forgot for some reason that acceleration would be in meters per second squared. Mathematically, you would arrive at it. So if we got that one, we'd also have number 8, right? For number 8, which of the 3 formulas would we use? Yeah, the one written F equals MA. Good. And we're almost...
10 instead of 9 on this one.
You want to do 10?
Yes.
Okay. So 10 as fast as I can. Shh. Number 10 as fast as I can. The extra conversation really is bothersome. And the chair has 4 legs. Okay. Or they're just the skids. No, yours has 4 legs. Okay. A cyclist rides 300 meters north in 60 seconds, then turns around and rides 100 meters south in 20 seconds. What is the cyclist's average velocity? Not speed. Velocity for the entire trip. Didn't they backtrack? Okay, so remember, velocity is displacement divided by time, not distance traveled divided by time. So how far did they actually end up going? 200 meters north. They went 300 meters north, then back 100 meters south. So they went 200 meters north. Okay? By the way, what formula are we using? Velocity? Okay? What's the average velocity for the entire trip? Well, we have a change in displacement of 200 meters north. Does that make sense? And then we divide the displacement, the change in displacement, by how long it took. So what was their total time it took? 80 seconds. So we're going to end up with a velocity of, what's 200 divided by 80? 2.5? 2.5 meters per second north is your average velocity.
How come you didn't have the square for that one?
Because that's not an acceleration. We had a change in position, right? So we ended up with a displacement of only 200 meters north. But there's no change in rate that we're dealing with. We're doing an average here. So you only have 1 unit at a time. Over the whole trip, they averaged 2.5 meters per second as their speed. And if you add that they ended up north of their original position, you take the north on too. Good? Good? Everybody good? We're going to do another one tomorrow. They'll flip the formulas a little bit, though.